I'm given g of x is equal to square root of x times sine 1 over x. I know that sine is between -1 and 1. So square root of x times sine 1 over x will be between negative square root of x and square root of x. So if I look at my graph, I'm going to graph my square root of x. I'm going to graph my square root of negative x. Now let's look at the domain. We know the domain for square root of x. So if we're just looking at square root of x, that is x greater than or equal to 0. And if I look at sine 1 over x, the domain is anything except 0. So it's all x such that x is not equal to 0. So if I combine these two, so one way I can do that is by looking at a number line. Square root of x, I'm going to do in green, is everything greater than or equal to 0. So this is for square root of x. And then for sine 1 over x, it's everything except 0. Since I can't divide by 0. So if I combine these two, I look at the intersection, and the intersection is clearly over here. So the domain will be strictly positive. So that means I'm going to be in the first and fourth quadrant bounded by square root of x and negative square root of x. And one thing to notice is sine oscillates between 1 and -1. So turns out it's going to look something like this, and then etc. So it just keeps oscillating between these two bounded functions. So now let's answer a few questions. First, what is the limit as x approaches 0 from the right of g of x? So the way we're going to do this is by looking at this inequality over here. If I look at the negative square root of x and square root of x as x approaches 0 from the right, I notice that the limit is just 0, because that means I'm coming from the right over here, from square root of x, and I approach the point 0, and then same thing with negative square root of x, I'm approaching it from the right, and I land at the same point 0. So by the squeeze theorem, g of x also has to go to 0. Okay, next question is, what happens if I approach 0 from the left? So if I come here from the left, what happens to g of x? Well, g of x is not defined for x less than 0. It's only defined when x is greater than 0. So the limit will not exist. And then same thing with square root of x and negative square root of x. It's only defined when x is greater than or equal to 0 for those two functions. So since it doesn't exist to the left of 0, we say that the limit as x approaches 0 from the left does not exist. And so if we look at just x equals 0 now, so as x approaches 0 for g of x, well, from the left it doesn't exist, from the right it's 0, because those two do not agree with each other, we say the limit does not exist. Let's look at another one. I'm going to be given a piecewise function, so we'll call it f. And f will be x cubed if x is not equal to 1, and 0 if x is equal to 1. So let's graph this. At x equals 1, I want it to be 0. And the rest is going to be like x cubed. It'll be something like this. So let's look at the limit as x approaches 1 from the left of f of x, the limit as x approaches 1 from the right of f of x, and then the limit as x approaches 1 of f of x. First we'll look at it from the left, so that means we'll be coming from the left here. So as we come to the left, we get closer and closer to this hole right here, which is at y equals 1. And then if we approach it from the right, coming down here, we get closer and closer again to the hole, which is at y equals 1. And since the left hand and the right hand limit are the same, the limit as x approaches 1 is also the same. And let's look at another one. Given f of x is equal to 1 minus x squared if x is not equal to 1, and 2 if x equals 1. So if I graph this, I know at x equals 1 it's going to be 2. And 1 minus x squared is going to be a parabola facing down. So let's see. So the roots are going to be at -1 and 1. And there's a hole going to be at 1, 0 there. Okay, let's see the limit as x approaches 1 from the right of my function, limit as x approaches 1 from the left, and the limit as x approaches 1. So from the right, I'm going to be looking at the right part of the graph. So it's going to be from down here. As I get closer and closer to 1, I approach the hole, which is at 0. And if I approach it from the left, I get closer and closer to the hole, which is 0. And because the left hand and the right hand limit are the same, we say that the limit is also 0. Okay, let's do another one. Let's say I have f of x now be square root 1 minus x squared, 1, and 2. So with 2, if x is equal to 2. So 2 is one of the points, and then 1 between 1 and 2, and we're including 1, but we're not going to include 2. And now it's going to be square root 1 minus x squared, which is going to be a semicircle or sorry, not a semicircle, a quarter circle. Let's try that again. Something like that. So now we want to see first what are the domain and range of f. So the domain is all possible x values. So the domain, we know we start at 0, so we want to include 0. 1 is an interesting point. So the bottom here, 1 doesn't exist, but at the top here it does. So that gets overwritten. So 1 will be included. And we go all the way to 2. So at 2, from the top here, we include it. The bottom we don't. So since we include the top, the domain has to go from 0 to 2. So every value from 0 to 2 will be taken care of. There's a y value for every x value. Okay, the next question is, at what point c, if any, does a limit as x approaches c of f of x exist? Okay. This one's a little tricky. And by the way, before we do that, we want to also find the range. Forgot to do that. So the smallest value is 0. That's over here, but it's not included. So we're going to put an open parentheses. We go all the way up to 1 here. And then we also want to include this point here at 2. So we're going to just put 2 like that. So it's between 0 and 1 and 2. Okay, so next question is, we want to see when this limit as x approaches c of f of x exists. Well, let's see. From the left, it won't exist. So at 0, it doesn't exist because from the left, there's no function there. The function doesn't exist. So we don't want to include 0. So we're going to start at 0. So everything over here between 0 and 1, not including 1, the limit will exist. At 1, the limit doesn't exist because from the left it's going to 0, from the right it's going to 1. And now everything between 1 and 2 will exist. But we don't want to include 1 and 2 because 2, there's nothing to the right of it, and 1, the left-hand limit is going down to 0. So the interval we're looking for is from 0 to 1 and 1 to 2. The next question is, at what points does only the left-hand limit exist? So left-hand limit, so here, let me redraw this. So left-hand limit, let's see. At 0 here, it doesn't exist since the left hand, there's no function to the left hand of 0. So we don't want to include 0. At 1, the left-hand limit is 0. So that works. Let's see, anywhere in this interval doesn't work. So actually, yeah, actually at 2 here, there's nothing to the right of it. The left-hand limit will work. And we don't want to include 0 actually because the left-hand limit exists, but so does the right-hand limit. So let's be clear about this. So x approaches 1 from the left will be 0. So that's this coming down here. And x approaching 1 from the right will be 1. Will be this point right here. So both the left hand and the right hand limits exist. So we can't include 0. So the only answer will be 2. And finally, at what points does only the right-hand limit exist? So let's see. Over here, the right-hand limit doesn't exist since there's no function. At x equals 1, the right-hand limit and the left-hand limit exist, so that doesn't work. So the only point will be at x equals 0. So at x equals 0, only the right-hand limit exists. And notice for these problems, for these last 2 questions, I did not include anything in between 0 and 1 and 1 to 2, because there the left-hand limit and the right-hand limit exist. So we're only looking at basically the start of an interval and the end of an interval. So like, think of it as from 0 to 1 here, that's like one interval, and the other interval is between 1 and 2. So the only interesting ones are at the ends of these intervals.